This is the historic 4th Ward Park in Atlanta, Georgia. It's got all the stuff you could want a park to have. Landscaped walkways, benches, grassy fields, a playground, and even a splash pad and amphitheater. The focal point is the 5-acre or half a hectare pond running through the middle. But this pond isn't just for looks. In fact, this park would have never been built at all except for the fact that it solves a serious flooding problem. For years, the 4th Ward neighborhood struggled with drainage and flooding issues. In the 90s, the city came up with a plan, a massive underground tunnel to carry runoff away. Don't get me wrong, I love flood tunnels. I have a whole video about them, but they're not always the right call. One engineer in Atlanta had a better idea, a solution that would address the flooding issue for a lower cost and significantly beautify the area, a rare opportunity to improve form and function. You've almost certainly seen a stormwater pond, whether you realize that's what it was or not. They kind of blend into the urban landscape to the point where they're basically hiding in plain sight. Some have been turned into amenities in places like parks where the primary purpose is disguised. But I think it's fair to say that no other single solution has been installed more extensively in modern cities or delivered greater cumulative protection against runoff than the humble stormwater pond. Let me show you how they work with a model I built in the garage and some of the ways these ponds are evolving in the 21st century. I'm Grady, and this is Practical Engineering. The problem that stormwater ponds solve is pretty easy to understand. Storms bring water, and that stormwater has to go somewhere. Spray a garden hose on some grass and some concrete and just watch what happens. How much of that water soaks in and how much runs off the surface. Depending on the type of soil below the grass and the duration of the experiment, the answers are pretty different for the two situations. Let's do a little development to make this clearer. Say we buy up this piece of land on the edge of the city. Add roads and sidewalks, some commercial parcels with parking lots, a park with a gazebo, tennis and basketball courts, apartments and homes with roofs, driveways, patios, and sheds. Before our project, this entire area was natural ground, soil that could absorb at least some amount of precipitation, allowing it to infiltrate into the earth, recharging aquifers. Now it's covered in all kinds of impervious surfaces. Let's see what happens when it rains. Essentially, two things can happen to rainfall when it hits the ground. It either soaks in or it runs off. How much of each happens depends on quite a few factors. For soil, it matters what kind. Sandy soils with large particles and interstitial spaces can absorb a lot. Clays with microscopic particles and almost no voids, very little. It also matters how much water is already in the soil. If it's wet before the storm, there's less room for more water to flow in. And as soil absorbs water throughout a storm, its ability to infiltrate more decreases. Any water that can't infiltrate the soil will run off into creeks or rivers nearby, but for impervious surfaces like asphalt, concrete, and roofs, there really aren't any variables. Essentially, all the water that falls on them runs off. When it rains in our new development, all the runoff still flows to the same place, maybe into a channel that runs into a creek that eventually connects to a larger river. It's just that now there's a lot more of it. As I mentioned, depending on the type of soil and the size of the storm, the difference between pre- and post-development conditions can be pretty significant. But a single development usually only represents a small portion of the watershed for a creek or river. So even with all these new impervious surfaces, the marginal increase in water levels during a storm downstream may be fairly insignificant. But zoom out to the scale of an entire city and the problem becomes obvious. It's basically all impervious. Development left unchecked can dramatically increase the frequency and severity of flooding because when it rains, a much greater proportion of that rain runs off into creeks and rivers instead of soaking into the ground. So most cities don't let development go unchecked, at least from a flooding standpoint. Rules vary a lot among cities and across the world, but the most basic requirement you'll see in most places is pretty simple. to get a building permit to develop a piece of property, you're going to have to limit the peak runoff from the property to pre-development levels. That means that for a given storm, on a given site, you can't have a higher flow rate after development than it would have been beforehand. Most development is going to involve adding impervious surfaces, whether they're roads, buildings, sidewalks, or parking lots, and that means more runoff. You can't just get rid of the water in most cases, so somehow you're going to have to store it and release it gradually to keep the peak flow below pre-development levels, and the simplest way to do it is a pond. This is my garage-built stormwater pond. It's just an acrylic flume I use for some of my demos, but I've built this outlet structure that should slow down the water, backing it up into the pond. All the acrylic for this structure came from my friends at SynCutSyn, this video sponsor. I just love this service. They give anyone with a CAD file access to laser cutting, CNC machining, bending, powder coating, and more. They don't have minimum quantities. Each of these parts was a batch of one. It's super fast, super easy, made in the USA. They make my life so easy and they support the show. If you need parts made from metal, acrylic, or a long list of other materials they have available, give them a try at the link below. I'm measuring flow with a meter on the inflow pipe. I also have a level sensor measuring the volume of discharge over time in this tank below. These are both feeding into an Arduino so we can look at the data. I'm going to simulate a storm event using this valve. So this is a handcrafted artisan inflow event. A typical storm has kind of a bell-shaped runoff curve. Starts slow, builds to a peak as more and more of the watershed contributes, and then tapers off as the storm moves away. And you could see that my stormwater pond captured some of that peak. Because of the outlet structure that has a small hole at the bottom right now, the discharge from the pond is much lower than the inflow. And after a little post-processing, I can show you the data. This is a plot of flow versus time. Inflow is the solid line, outflow is the dashed line. The units are arbitrary since this is just for comparison, but I did calibrate the sensor so they match as closely as possible. You can see that the area under both curves is the same. Just as much water came out of the pond as into it, but the peak outflow rate was a lot lower, and that's a big deal. The peak of the flood is everything. That's what determines how high the water rises downstream. It correlates closely with the total amount of damage that occurs. So most drainage rules in cities don't really focus on total volume, they focus on the peak flow rate leaving the site. And you can see that the peak coming out of my pond is significantly lower than the peak going into it. So great, the pond did its job. Problem solved, right? But you know this wouldn't be an engineering challenge if there wasn't something to balance. You can imagine a pond with no outlet at all that just fills up with runoff. In that case, the peak discharge is 0. We've maximized the performance, right? Obviously not, since that storage is expensive not only in the construction cost to build it, but also in the valuable real estate it takes up on the site. So really, the optimal solution is the one that uses the least volume necessary while still keeping the peak discharge below what it would have been without any development at all. The problem is, storms vary in intensity and duration. So most of the time, you're going to have to show that your design works for several different storm events of varying magnitudes. A little hole at the bottom of the outlet structure might work for a small one. However, for a large storm, you can see that my pond fills up pretty quickly and eventually overflows. Sure, you can make the pond bigger to hold more volume, but we're just trying to trim the peak off the flow rate to match pre-development conditions. We can release more water from the pond, we just have to be careful about how much. When I remove this conspicuous piece of tape from my outlet, you can see that I've already built this in. I have a larger hole higher up on the structure so it can release more during more intense storms. Let me simulate that now. You can see as the water reaches that level, the flows from the two holes combine, and we get more water released from the pond so it doesn't overflow. Here's the graph of the small storm again, and here's the graph for the big one. You can see that in both cases, we're not completely eliminating the flow. The pond and the outlet structure are just shaving off the peaks to reduce the impact of the impervious surfaces. But that can be a tricky thing to do when you have a lot of different storm magnitudes to consider. Take a look at stormwater ponds in the wild and you'll start to notice the wide variety of outlet designs. Placing the various orifices or weirs is kind of an art as much as it is a science, because every site is different and every city has different rules. An engineer has to tune the structure to balance the amount of storage with the additional runoff from all the impervious surfaces. I added a third hole on top of my structure so it can handle a really big storm. The flows through all 3 holes in the outlet combine to create more flow out of the pond. Here's a graph of that run. You can see the discharge is much higher, but it's still below the peak inflow. But this gets quite a bit more complicated because stormwater runoff doesn't just create flooding, it also carries pollution. We think of rain as cleansing, but the stuff rain washes off the landscape has to go somewhere. That means everything from trash, oil, dog poop, sediment, road salt, and a whole lot more ends up in creeks and waterways. A lot of the contaminants in stormwater are either attached to sediment or are sediments themselves, so stormwater ponds can serve double duty, reducing flooding and downstream contamination. You're not going to get the water really clean like at a wastewater plant, but the treatment for suspended solids can be as simple as letting water sit still for a day or two so bits of stuff can settle to the bottom. You may have heard the terms detention pond or retention pond. We've been talking about detention ponds that simply slow down runoff, but they eventually empty out. Retention ponds are related, but they keep some of the water stored permanently, and it makes a big difference when it comes to treatment. Let me show you in the model. I added a bunch more mica powder to the water so you can easily see how the water flows through the pond. Contamination is worse during the beginning of a storm, sometimes called the first flush, when streets and surfaces are dirtiest. You can see in my model, before the pond starts filling, everything suspended in the water is making it through to the outlet. The water's moving pretty quickly and it's relatively turbulent. There's just not enough time for anything to settle out. But I can put a plug in the bottom outlet of the structure and pre-fill the pond so it acts like a retention facility. Now when I turn on the pump to the same flow rate, you can see a big difference. There's a lot of turbulence where the water flows in, but things slow way down toward the outlet. It's just a scale model, so most of the mica powder is still suspended at the end, but you can imagine if we scaled this up so the water took several hours or more before reaching the outlet, most of the solids in the flow would have enough time to settle out. And retention ponds have other benefits too. They help with groundwater recharge by giving water more time to soak in, and they often look nicer, since water features are an amenity, and these are landscaped like any other pond you might intentionally install on a site. But obviously, there's a trade-off here. You get cleaner water out, but you need a bigger pond, since some of the volume is already taken up before a storm arrives. However, there is a way to have your pond cake and eat it too. Outlet structures don't have to be passive like my demo here. Imagine if you could actively control how much water flows out of the pond based on sensors and weather forecasts. You could hold water in the pond for longer periods of time when there isn't too much rain, improving the quality of the treatment, and then pre-drain the pond ahead of a storm, freeing up that space for the next runoff event. This is known as continuous monitoring and adaptive control. It's basically smart stormwater management. It is a pretty cool idea that's only just starting to catch on in cities, but it has disadvantages too. One is disease vector control. Because there's no stable pool, you can't reliably stock fish to eat mosquito larvae, so there are limits on how long you can hold water before you have to drain the pond. It's also quite a bit more technically sophisticated, so there's a trade-off there too. Usually these types of systems are operated by specialized companies that install, manage, and maintain them. Some even sell the capacity on an open marketplace, allowing developers to buy credits in lieu of on-site ponds. This stuff gets pretty creative, addressing the lot level needs of individual developments with larger watershed scale outcomes. And in fact, they're often part of a larger idea called regional detention. Even though on-site detention or retention is great in theory, it can be messy in practice. Small lots don't have room for meaningful storage. Building dozens of tiny basins inevitably leads to uneven maintenance. The small pipes and outlets of minor ponds are more susceptible to clogging, and in some cases, they can actually make flooding worse. You could see on my graphs that detention lowers the peak at each site, but it also delays it. If mini basins are designed with similar outlet controls, their attenuated peaks can arrive all at once at a confluence downstream, spiking the creek level worse than if there were no detention at all. Water quality benefits are hit or miss too, because performance depends on how each little system is built and maintained. So there are cases where developers get together, or a city or a drainage district solves the problem at a regional scale, building a single, larger facility that can handle the runoff from multiple sites. By routing excess runoff to a shared basin, or a network of them, you gain real storage volume, coordinated release rates that match downstream capacity, and professional centralized upkeep. It also lets you optimize water quality treatment and pipe sizes across the area instead of overbuilding each parcel. Keep the small storms where they fall for infiltration and local benefits, send the larger pulses to regional detention so the watershed sees a calm, controlled hydrograph instead of a patchwork of ponds releasing a chorus of overlapping peaks. I should make clear that detention and retention are far from the only stormwater management tools. Regional geology and hydrology often drive the design. I live near Austin, which has strict environmental rules because of the Edwards Aquifer. Where the limestone reaches the surface, contaminated runoff can easily enter the groundwater, so many sites in Austin require filtration ponds that actually pass water through a layer of sand before it's discharged downstream, removing pollutants before they can reach the groundwater. I've talked about permeable pavement in a previous video, and there are a lot more solutions out there. Many civil engineers spend their entire careers solving urban stormwater puzzles, trying to balance the important watershed functions with the challenge of flooding and pollution. Detention and retention ponds are just one piece of it. Part park, part plumbing, mostly hiding in plain sight, they're often carefully tuned pieces of infrastructure that help keep the city's head above water.